Today we are going to explore work, power, energy. Yeah, work, power, energy. One by one, we have a separate part about work and separate part for power, separate part for energy. First, we are first of all we will start from from work. Yeah, your heard is right. We will start from work. Now, let me start with question. With question. What do you think about work in physics language? One thing I would say there is a huge difference between about work from real life. Okay, about work from real life. There is a huge difference. Use. During this lecture, you will hear a lot of times theta, rotation, angle. Yeah, angle will matter. Angle will provide a negative, positive sign. According to angle, you will find your work is positive or negative or zero. It's all about angle, vector. Apart from this, there are a lot of things. Okay, there are a lot of things. Now, as I told you, we are starting with meaning of work. With the meaning of work. Look, during this lecture, during each lecture, whenever I look downward like this, so you understand that yes, I am reading PPT. Okay, PPT. I have a PPT. This is a board, but not a digital board. Okay, so if I write all those definition, all those sentences, then it will take too much time. Okay, so I don't want to take too much time. That's why just I will write, and my focus will be on teaching. My work over here is to tell important points, is to teach every topics, every main words. Okay, so look at me. Look at me. PPT is saying work is a scalar product. Look, this is W, which is known as work. Just we represent this work by capital letter W. Okay, whenever I will write like this W, so just understand yes, this is a work. Okay, so work is a scalar quantity. Okay, first point about work is it is a scalar quantity. Work means what? We do something. Yeah, we did something. We will be doing something. That is what work. Over here, you need to understand it is nothing but this is a scalar quantity. A scalar quantity means it will have it will have uh, it will have a magnitude and unit, but not a direction. This is the meaning of a scalar quantity. Clear? Clear. You know, formula for is Fs, Fs, F into S. Try to understand. F into S. F is over here, force, and S is the displacement. Work is a scalar product of force and displacement. A scalar product. You must have heard a word, a scalar product, which means we are going to multiply. We are going to multiply the two vectors, and when we multiply two vectors, then third result vector comes as a scalar vector, so this is third, which is a W, is a third vector, which is a scalar quantity. But force is a vector, and S, which is a displacement, is also vector. I'm not going. Okay, if you want, then yeah, let me explain. Here we know that multiplication of a vector. If we will take two vectors and multiply them, then third vector can come as a scalar. This happens. Okay, this can happen. So that's why we say that multiplication of a two vectors is coming as a third vector, which is a scalar quantity. So this will be known as a scalar product or dot product. Okay. On the other side, there are two vectors uh, whose multiplication is what after multiplication uh, third quantity is coming, which is vector. It happens. So if multiplication of a two vector is coming as a third quantity, which is a vector, will be our vector product. Okay, or you can say cross product. But right now, in this lecture, our full focus will be on a scalar product. Okay, a scalar product. So W is equal to F into S. F is a force and S is a displacement. Try to understand meaning of this equation. It is saying W is equal to Fs. Means if you apply force on object, okay, you will apply in real life. We apply a lot of force, isn't it? We apply a lot of force on objects. What happens? What happens with object when we apply force? We see that object is moving, object is covering distance with respect to time. It happens, yeah. So if you apply force and then object displaced, okay, after applying force, if object covered a distance, then yes, in the language of physics we will say yes, work done is not equal to zero. Okay, work done is something over here in this field. Okay, but what if force is a zero? Let's just say you applied a zero force. So in this case your work done would be zero. If you applied 2 Newton, but there is no displacement is zero, then again you would say force work done is a zero. Reason is, if displacement is a zero and force is not equal to zero, then your work done will be what? Zero. If you multiply zero by some number, then result would be zero. Okay. Okay. Now next, unit is what? F is a Newton, so unit would be n meter. S is for displacement. Okay, so unit for work would be Newton meter, or we say that this is joule. Okay, joule. This was the unit. Dimension would be what? Here m kg is not present over here, so m and L means L is how much? L is a 2. L is a 2. So you can ignore right now dimension. Just understand. If remember, we will see two types of a force. One will be constant force and second would be variable force. First of all, right now we are going to explore force constant force. Okay, force constant force. So if in this case F into S, if a force is a constant, remember, if a force is a constant means force is not changing. Let's say I applied a 12 Newton force, okay, on the object, but distance is changing, but force is not changing. 12 Newton is for all the times. After 2 seconds, the Newton is the same, but the displacement is 4 meter. Displacement became 4 meter. After 3 seconds, 6 meter, but Newton is the same, 12 Newton. So this is known as our force constant. Okay? Here F is a constant. If F is a constant, just this F will be outside. This F will be outside when you do integrate. Okay. But force for force constant, you don't need to apply calculus. Okay. For variable, yeah, you will have to apply calculus. So over here, work done is equal to force multiple distance moved in direction of a force or component of a force. Try to understand. Try to understand. Here direction is very compulsory. Direction for force I am telling you. For force, direction is compulsory. If I am applying force in this direction and object is also going in the same direction, it means angle is zero. Okay, it means angle is zero. So angle between force vector and this displacement vector is how much? This is what will be our angle. Okay, angle between force and displacement vector. This angle you will take. Clear? Or component of a force. You will have to observe that yes, component we resolve a result vector into two components x and y. So you will see that yes, this component bringing our object uh, forward, yeah, or another component of the resultant vector is bringing upward. That is what you will have to observe according to question. If a question is giving this, so tell me object is moving horizontal. So of course, if our object is moving horizontal, you will take what component? You would say horizontal component. Yeah, you don't need to care about vertical component. When question is saying object is moving horizontally, then okay, then you don't, your focus should not be on a vertical component. Clear? If object is saying a lift is going upward, object is going upward, in that case here you can see, and force is also upward. So when we are applying force upward, then object is going upward. So which one component is bringing this which one component of a force is bringing the object upward? You would say vertical component. So you take a vertical component, not horizontal component. Okay, not a horizontal component. This was about component. When force and displacement are inclined to each other, yeah, this is also important. Inclined, which means there would be angle like this, inclined over here, and the object will be placed like this. So this figure is known as inclined plane. We will get angle. All the times you see in your in your real life, you say that it is not impossible. I would say this is not possible for all the times that just we bring object upward or horizontal. No, we also bring object up by making an angle with horizontal. Yeah, this happens. I bring like this, like this. I bring like this. So this, over here we are making an angle with horizontal. So in that case, you would say, I am not bringing upward. I am not bringing exact horizontal. Yeah, I am moving the object. I am bringing the object between x and y axis. That is what is happening over here. Yeah. So if an object is moving between two axes, we say yes, there is an angle between them. Then an angle will matter over here. Angle will matter. So if angle is coming, okay, angle is coming in your equation, then just add cos theta over here. W will be equal to F S cos theta. F S cos theta. Now try to understand how did cos theta come? How did a cos theta come? My answer would be, we know that this is a scalar product. So for a scalar product we have cos theta. For vector product we have sin theta. Okay. Over here, this was valid when angle was 0. This was valid, W is equal to F into S. This was valid when angle was 0. But now we have an angle. So for angle we apply cos theta. Clear? We will apply cos theta. If you put over here cos theta, then this will become F into S multiple 1. Then at the end we will have the same equation. W is equal to F into S. Clear? So it's your choice. If you want to write over here cos theta, you can write. You can write. Here you understood that if angle is coming in our equation, then we will just add this cos theta. Cos theta is a 4 angle between two vectors. between two vector, force and displacement. Clear? Clear. Now next, some points. Remember, if theta is acute, then understand our work is a positive. Clear? If theta is obtuse, then just understand our work is a negative. If theta is a right angle, or you can say 90 degree, exact 90 degree, then our work done will be zero. Okay, this is fact, but how to visualize practically? Okay, let me explain. Look, if you put a value of 45, uh, 45, then what will be cos 45? Positive value will come. Positive value. Whereas if you put 120, so automatically cos 120 will come as a negative number. That's why we say that our work will be negative. Clear? Okay. What about theta is 90 degree? Here we are understanding that the force is a downward like this. Force is a downward, and displacement is also downward. Displacement is also downward. But no. This is not example for 90 degree. This over here. Over my head, I am bringing a cylinder, a small cylinder. Okay, not then some books. I am bringing some books on my head, and I am going into another room. I am asking what will be work done by me. Work done by me. So your answer should be what? Here, force I am applying upward on the books upward, and displacement is horizontal. Force is vertical and displacement is horizontal. So angle is how much? 90 degree. So if you put a cos 90, then what will be value? You would say 0. So f into s multiple 0 will become 0. So that's why we say work done will be 0 when theta is a 90 degree. Clear? If you put theta as a 180 degree, then you will see that negative value will come automatically. That's why in starting I was saying that if you, it's all about angle. Okay, angle vector. Okay, vector. When it comes to work. Now next, work done by variable. If a force is a variable, try to understand. If a force is a variable, uh, F and X. X is for displacement. So x1, x2. This is our curve. Try to understand. This is our curve. When in our graph line, when graph is providing a curve line, not straight, just understand this curve. You can see it is changing. Yeah, sometimes it is a decreasing, then increasing, decreasing, increasing. This is known as variable. If it is a state, you can see force is the same, but displacement is changing. Force is a constant, and over here force is changing according to displacement. With respect to displacement, you would say over here this will be our a small x, a small distance, and this will be f1, again f2, f3, f4, f5, f6. Question is asking just a small distance. This is a small distance dx. Over here, what is our instant force when we are taking this a small dx, the small distance or displacement? Then over here, what is our a small force? Not a small, but instant as force. Okay, instant force. First of all, just understand. Over here, force is a variable, not constant. How? This curve is a changing. It is changing all the journey. Here, during this journey, this curve is changing itself. Yeah. So that's why force is a variable. Over here, force is a F1. If over here 12 Newton, so F2 would be something else. F3 would be something else. 30 Newton. F5 18 Newton, like this. So force is it can be decreasing, it can be increasing. Sometimes question will be asking our total work done by this graph would be what? From x1 to x2. From here to till here, what would be our complete work done? So there is a separate formula. When it comes to variable, we use calculus. So total area is our. Remember, total area is our work done, or you can say change in momentum. So from x1 to x2, you have two options. First is f1 dx1. Am I correct? f2 dx, f3 dx, like this till the end. fx, not x but n dx. This is your first option. You will add, okay, you will add all this a small distance. But you see it carefully. Don't you feel that this is it will take too much time? Of course, extremely too much time. So there is another option, or you can say second version of this first option. We have, which is a total work done is equal to, limit we will take from where to where. So from x1 to x2. Just to be look at it. Okay. Now total f. So this will be our fx. Total f into dx, a small part. Just we are finding this dx and this is small. When you will put this limits, you will get total work done. Okay, total work done. This is our second version of the first part. Total work done is equal to integration from limits, then f into dx. Here we add d for a small part. When we will use this limit, it means we are finding total work done. Okay, we are finding total work done. One point from this graph you have to keep in your mind, which is area of this graph of apex. You can see apex where x is a displacement. So remember, f s will provide something else. Okay, s is a displacement. So f x will provide total work. Okay, total work done represents work done. Apex represents work done. This is what is the first point from this graph that you need to remember for future. Next point. If a displacement is in vector, then dx is replaced by dr. ds we will replace by dr. Over here, if displacement is given in the form of a vector, okay, in the form of a vector, so just replace that s by r. R is a 4 position vector. Okay, r is a 4 position vector. So our reference point, as usually majority, our reference point will be r, not r origin. Okay, origin in the graph. Okay, so you use this dr when displacement is given in the form of a vector. Then if displacement is not given in the form of a vector, simple, then you can use a ds. Just put value. Now how to break this dr? So you know, r is equal to r I cap plus, not r but x I cap plus y j cap plus z k cap. This is very basic, yeah. X y z. So x is known as I cap, y is known as k cap, z is known as k cap. This was very basic. So our dr will be what? Dr. So dr will be d. Just add d. Okay, d. So dr will be dx I cap plus dy j cap plus dz k cap. Just we added a d. Dr means a small distance. Only r means only r. Dr means a small distance. Okay. So dx, a small dx. Here a small displacement which is along x-axis, and a small dy which is along y-axis. A small dz which is along z-axis, along z-axis. Okay, along z-axis. So dx, we are taking a small displacement which is along I cap. Dy which is also a small displacement but direction is upward. Okay, dz is also a small displacement but direction is forward and front of. Okay, so our work done will be from x1 to x2 will be here x, y, z. If all these variables are coming, then just understand this is our variable force. Okay. So if first fx dx, this fx dx, this dx, then next variable fy dy. Next variable would be fy dy. The next variable. So first of all, we will integrate first term, then second term, then third term, again and again. If a force is changing itself, then so fx, then add this. Over here we will have y1 to y2, fx, not fx but fy dy, plus z1 to z2, fz dz. Okay, this is our formula for work done, where force is changing itself. I hope you have understood. Now next we have conservative and non-conservative forces. Conservative and non-conservative forces. conservative. First of all, let's be clear about conservative forces. Then we will say non-conservative forces. Okay, so conservative forces. Force. It is a type of force. Okay, type of force. So work done by such forces does not depend upon path. Remember. So work done by such forces which does not depend on upon the path clear upon path like gravitational force. Gravitational force is a conservative force. It does not depend on path. That's why gravitational force was considered as a conservative force. If you are going like this upward, so over here we will just care about the vertical, not horizontal for gravitational force. Okay? So if you are going like this, so just don't care about this curve, just care about initial and final point. That's it. Okay, so for conservative force, here we will depend on initial point and final point. Remember, what done by such forces? Such forces which does not depend on path. Next sentences, it depends only initial and final position. Initial and final position. Initial and final position. Remember, if it is not depending on path, it means it is seeking initial point and final position. Am I correct? Next sentence is, if F is a conservative, if our force is a conservative, then WA will be equal to WB will be equal to WC. Look at over here. This is the best example, I think so, for conservative force. This is A object. Over here A object. This is B object. Okay. So force I applied in this direction. Force. This is path B, path A, and path C. Look at. It is saying over here, just we will see this location. This is shortest displacement. This will be our value. This will be our location. Like this, state. Okay, state, not curve. So if you go like this, then upward, downward, by curve. So our value will be this AB. So W work done by A will be equal to work done by B will be equal to work done by C. Work done by C. Whatever will be value of A, work done A will be also for work done B, will be also for work done C. Next, work done by conservative force in a closed path is always zero. Closed path means particle started moving from here and it went like this. It went to hotel, then seminar, then a school, college, and he came to the final position, which is initial. So A, B is over here. So this you can see it is making a closed path. So over here, if a conservative force is making a closed path, so work done will be for this work done will be zero. Reason is initial and final is the same. initial and final resistance. Examples for conservative are gravitation force. Yeah, we have seen a spring forces. We say a spring forces like this. So we will when we will bring this in this direction. What will happen? This will go uh, in opposite direction. So it has only, it will not go up or downward, not only horizontal like this, only horizontal. This is a exact location, okay, for a spring. So over here it is not depend on path. It is not depend. This is not depend on. It is not depend on path. A spring force, electrostatic conservative. We will say electrostatic conservative for when we will take this chapter, which name will be electrostatic force. Next we have non-conservative force. Non-conservative force. Non-conservative force. Try to understand. Whatever we saw about conservative force, just opposite it will be our non-conservative force. For example, work done by such force which does depend upon the both is for non-conservative. Initial final position. No, we will not care about for non-conservative force when it comes to initial and final position. So over for this non-conservative force, we will take actual path. Actual path. Did we take this object like this upward? So this will be our actual path, and this shortest path will be for gravitational. So this actual path is a non-conservative force, and this shortest path is a conservative force. Okay. So yes, non-conservative force depends on path, Clear? Over here, a WA will not be equal to WB. Work done depends on path. In a closed path, W is not equal to 0. Try to understand this. Over here, we saw that work done was 0. If a force is a conservative, then work done will be 0. If a force is a non-conservative force, so force is a non-conservative, and her length of this wire, let's say length of this wire was 20 meter. So our work done will be 20 meter. Work done will be 20 meter. Actual path we will take, which is 20 meter. Okay. The example, friction. Viscosity. This friction is an example of conservative. You know, friction is not possible without contact. Yeah. Even when we take air resistance will touch the object in the sky. So over here we are observing that yes, when object will touch the other object, then it is possible to get friction. Okay, so to get friction we should have contact between them. Okay, contact between them. Condition should be satisfied for conservative force. Have you understood till here? Have you understood? No. Energy. Definition of energy would be what? would according to you? According to you? Yeah, from my side, it is a capacity of a doing work. I have given you projects. So according to your capacity, I gave you project to complete that. So here I understood that yes, this is this much you have a doing capacity. You have a capacity of a doing. So doing capacity of a doing work is our energy. Okay, effort of a doing work is our energy. So energy of a body is its capacity to do work. Clear? In short, you can say. In short, you would say capacity of a body to do work is our energy. For example, 20 joule is a capacity of a body which can work only till the 20 joule. Okay, 20. So 20 joule is a capacity which is in amount. Okay. So capacity. When it comes to quantity, which type of a quantity is energy? Answer would be a scalar. Work was also a scalar. Energy is also a scalar. Reason is it does not provide a direction. Yeah, no direction. We don't care about the direction when it comes to energy. Okay, so a scalar quantity. Remember, a scalar quantity when it comes to quantity. Clear? Dimension will be also same. Whatever was for unit will be also same. We saw that unit for work was joule, so unit for energy will be also joule. Dimension will be same. Okay. Whatever you take energy, unit will be same joule. Okay. For example, you take kinetic energy, potential energy, so unit is the same for all energy, for all type of energy. Clear? Do you know what is this? A is equal to mc square. So remember, A is energy, m is a mass, and c is the speed of light. We will say it later. It will be explored later in separate part. Kinetic energy with any reference must be positive. Whatever you are taking reference point for kinetic energy, okay, for kinetic energy, then take that value always positive. Always positive. This is a main point. Condition, or you can say condition. So kinetic energy, magnitude, sign of a magnitude of a kinetic energy should be kinetic energy with any reference should be positive. Clear? Should be positive. Kinetic energy, energy possessed by motion of a body. Yeah. Now we moved on kinetic energy. On kinetic energy. We have seen definition of energy. This is the capacity of a doing work by a body. Now when it comes to kinetic means motion of a body. Kinetic means motion of a body. This object can move this much. So we found capacity of this body. How? We found yes, it has this much kinetic energy to move till this kilometer, this meter. In short, you can say if a body is moving, it means it has a kinetic energy. If a body is moving, it has a kinetic energy. If a body is in a rest at height, it means body has a potential energy to convert itself into kinetic energy. Okay. So formula for kinetic energy, it is represented by Ke. K is kinetic, A is energy. So formula is a half mv square. Half mv square. Do you want to see derivation? Derivation? Yeah, derivation. So we have nice derivation. You know that K is equal to can be written as force. That's also force. Reason is joule is the same. So force is F into S. Am I correct? Yes. Force can be written as ma. Just we used calculus. Okay, calculus. So S can be written as D. S can be written as this is what? I think S is S. X by T, yeah? X by T. S. So A. Here we want A. So A will come V square minus like this. There is a derivation. So through this derivation you will get this equation, which is 1 by 2 mv square. mv square. Okay, mv square. Look at over here. V square is representing itself that object is moving. Here, try to understand. This k is directly proportional to 1 by m. 1 by m. 1 by m. If kinetic energy over here is, this is directly, you can write this like this, mv v square into m by m. Then we will get m square v square 2m. So this will become p square by 2m. This is a relation between momentum and kinetic energy. Momentum and kinetic energy. Between kinetic energy and momentum, this is our relationship. So it is equal to p square upon 2m. Here you can see 1 by m is directly proportional to kinetic energy. Clear? This k is directly proportional to 1 by m, or you can say k is inversely proportional to m. Okay, this is how we call it. So from this equation we can say potential will be equal to p square is equal to 2mk. So this will become 2mk. This is k. Just substitute value of k, which is 1 by 2 mv square. Which is 1 by 2 mv square. So 2 by mv square upon 2. mv square upon 2. P is equal to m square v square. This is our p square. This is our equation for calculating momentum, not potential, momentum. Where if equation is providing relation of momentum and kinetic energy, then and question is asking what will be kinetic energy, where potential is not potential, momentum is given, then this formula will be used. P is equal to under root of 2m kinetic energy. 2m kinetic energy. Clear? How did it come? This came from this equation, which is equal to P square upon 2m. Clear? Got it? Use this formula in your equation. Then say your. Then say over here P is a linear momentum. Next we have work energy theorem. Work energy theorem. Work energy theorem. It means total work done is equal to change in kinetic energy. This is the meaning of a work energy theorem. Okay. So total work done by all forces. Remember, total work done by all forces is equal to change in kinetic energy. When it comes to delta, change potential energy, kinetic energy, we start from a final minus initial. Yeah? So final kinetic energy minus initial kinetic energy will be equal to total work done by all forces. Clear? Total work done by all forces is equal to change in kinetic energy. So this delta Ke can be represented as Ke final minus Ke initial. You know that this can be written as 1 by 2 mv1, not 1. This is final square. You would say 2 minus 1 by 2 mv square. This is how we can write this equation into this form. 1 by 2 mv square minus, first is final and second and negative is a initial. Clear? In short, you can say delta W or work total is equal to change in kinetic energy, final minus change in initial energy. Clear? If work is positive, remember, if work is positive, it means kinetic energy is increasing. If work is negative, then just understand kinetic energy is decreasing. Now it's all about sign of work done. If a sign of magnitude of work done, total work done, is positive, just understand, yes, kinetic energy is increasing. If work is negative, kinetic energy is decreasing. Clear? Derivation of work energy theorem. We have derivation. Look at over here. Derivation part. Look at over here. Let force, not force, but let force be constant. Force here we are taking as a constant. Clear? In that case, what will be derivation for this force? So you know W is equal to A phase. How will it bring? That is what we are going to see. So W is equal to A phase, and we know F can be written as MAS. S is the displacement, and value of A will be what? V square minus U square upon 2S is equal to S. Try to understand. V square minus U square can be written as 2AS. Yeah, 2AS. Just we want value of A from this equation. So it can be written as V square minus U square upon 2S is equal to A. This is value of acceleration. Clear? Just we substituted value of A in this equation, and we got W is equal to M into V square minus U square upon 2S in 2S. So this S will equal to each other. Finally we have mv square. So this half 1 by 2 mv square minus 1 by 2 mu square. Final initial. U is the initial, V is the final. U V here. Okay, that is how this equation came. That is how. So this was your derivation. Clear? This is valid when force is a constant. Remember, when force is a constant, then the equation is valid. What if we later force be variable, then look at over. Let force be variable. So W, when it comes to variable, we use calculus. Yeah, we apply calculus. When force is a constant, we don't use calculus. Simple this thing. Okay, simple this thing. So W is equal to x1 to x2. F dx, which is equal to here value of f will be ma dx. Look at over. So tell me, can we write a as a dv upon dx? Am I correct? I think yeah, v is over here velocity. dv upon dt, yeah. So dv upon dx. We know that acceleration can be written as a is equal to dv upon dt or dv upon dx into v. So this is dv upon dt multiple dx upon dx. So dv will be as it. So dx upon dt will be our v and dx as it. So over here we have x1, x2. So value of m will be as it. M is a constant. Okay, if m is a constant, so value of a will be dv into b upon dx. Clear? Okay, got it. Dx, and we have this dx will cut to each other. So finally, m is a constant. Remember, m is a constant. Integration of a dv will be v. So v multiple v will be our v square. Okay, v square x1, x2. Okay, remember, integration of a single variable whose degree is 1, then will be what? Same x. Integration will be same x. V square upon 2. 2 is a compulsory. Upon 2. Limit would be from x1 to x2. Clear? From x1 to so 1/2 will come outside over here. 1/2 f v final square minus v initial square. This is when force is a variable. W is equal to 1/2 m when force is a variable. Okay, just see m half mv square initial x1. This initial final and initial. Okay, final and initial. 1/2. This 1/2 m as it. Then we have this final. Final is this x2. Final minus initial. So final minus initial. That is how this came by doing integration. Finally, you can write total work done x1, x2, f into dx is equal to 1/2, or you can say change in kinetic energy k if E K is inertial, which is equal to 1 by 2 m v final square minus 1 by 2 mv, not mv but inertial square. This work done is equal to final kinetic energy minus initial kinetic energy is equal to 1 by 2 mv square final minus 1 by 2 mv square inertial. Got it? Now next point, potential energy. Next we have potential energy.